Hello and welcome to Uncomat Online Academy. Today we have probability and we want to continue from where we stopped in the last lesson. In the last lesson we talked about independent events and we said that independent events is where the outcome of the first event affects the outcome of other events. That means that if we have two events, what happens in the first event will affect what will happen in the second event. Today we are going to focus on dependent events. Dependent events. So we are going to learn the meaning of dependent events, types of dependent events, expression for dependent events, and of course we are going to solve examples on this. Now, dependent events. What do we mean by dependent events in probability? A dependent event is when we have different events and what happens in one of the events affects what will happen in the other events. You have different events and you have samples. Maybe you have a sample to pick. If you pick one sample, it will affect the number of samples available for you to pick again. That is what we call dependent events. Take for instance, if you have 3 oranges in your bag and you give somebody 1 orange from the bag without replacing it, you will find out that the total number of oranges you have in the bag will reduce from 3 to 2. You have 3 and you give somebody 1, then it will remain 2, or else you replace it. So that means that if you want to pick again, which is the second event, giving somebody or picking an orange from the bag is an event. The orange you are picking is the sample. So from the first event, you picked an orange out of 3 and now remaining 2. Now that means that if you want to pick another orange, which is another event, it means that you are going to be selecting from 2 instead of 3. In the first event, you selected from 3 oranges, but in the second event, you are now selecting from 2 oranges because you have given somebody one of the oranges. This is what we call dependent event. You can now see that the orange that you gave to somebody in the first event has reduced the number of oranges you now have in the bag for the second event. Now we have this expression for dependent events. The expression for dependent events is that the probability of A and B, where A and B represent first and second events. Of course, remember that this event can be more than 2, but to make things easier for us, we use only 2 events. We are considering only 2 events here. Now, the probability of A and B, that means the probability of the first event and second event, or result of first event and result of second event, is equal to the probability of the first event plus the probability of what is remaining after the first event. That is the probability of B remaining. Like the orange we picked in the instance I gave, you pick an orange and it will reduce the total number of oranges or samples available. So in this expression, B remaining is showing you what is remaining, the total number of the samples remaining that is available for you to pick from again. So this is the formula, and that is P, probability of the first event, times or multiplied by probability of the second event. It is very important for you to know that the separation between the first event and second event here is multiplication times. Now let's look at types of dependent events. We have two types of dependent events. We have dependent events without replacements, dependent event without replacements, and dependent event with replacements. In a dependent event without replacements, we pick a sample and the sample is not replaced. So the sample is not reusable or is not reused in dependent event without replacements. You pick a sample and that one is lost forever. But in a dependent event with replacements, you pick a sample and you put it back into the maybe the bag or where you picked it from, making the sample available again for you to pick from. That is what we call dependent event with replacements. Of course, something like this can occur. Maybe you have different coins in your pockets. You have 50 kobo, 100 kobo, and 25 kobo coins. Assuming you have all these things, all these coins in your pockets, and you want to pick 50 kobo, then you dip your hand inside your pocket and you see that what you brought out is 100 kobo instead of 50 kobo you are looking for. Then you put it back inside your pocket and try to select another coin. Then you bring another one. You see that that one is 25 kobo and not the 50 kobo you are looking for. You still put it back and try to select another kobo. So that is what we call dependent event with replacements. Or when you have three oranges and somebody asks you for one, then you give out one of the oranges. But what you actually need is three, the one that you will take your own. Then maybe you go and pluck another orange and replace it, making the total number of orange again 3. So you give somebody one of the oranges and you replace it with another orange, making the total number of oranges in the bag to remain the same. That is what we call dependent event with replacements. You take and you replace it. Now this is a graphical illustration, a diagram to illustrate the difference between dependent events without replacements and dependent events with replacements. Now you can see that in this side, we have the same bottle is the first bottle and second bottle, but in this first bottle now, you pick the red sample and you pick a blue sample and the blue sample is not replaced, now making it to remain the total number of samples in the bottle to remain 3. That is why we have 3 samples in the second bottle instead of 4 samples because the first one you picked, you did not put it back to the bottle. So this actually shows that in a dependent event without replacement, the total number of the sample space will keep reducing after each event. If you pick without replacing it, it will reduce the sample space. Now, in this side, you pick a sample and you place it back. Maybe it is a coin, you pick it and you see that it is not the one you want. Then you put it back inside the bottle. When you put it back, then the total number of samples in the bottle will remain the same. So that is why we have 4 samples in the first bottle and second sample and 4 samples in the second bottle. So in a dependent event with replacements, the sample space remains the same. The sample space remains the same. That is the total possible outcome in a dependent event with replacements. It remains the same because what you pick, you place it back. Now let's look at some examples. In this example 1, a bag contains 3 mangoes and 2 oranges. If 2 fruits are taken from the bag at random without replacement, calculate the probability that the 2 fruits are mangoes, that the first is mango and the second one is orange. Now, this is an event without replacement. The one you pick is gone forever. Now, that means that since we have 3 mangoes and 2 oranges, now to solve question A, 2 mangoes, that the probability of getting 2 mangoes. We have 3 mangoes and 2 oranges. If you pick the first mango, picking from the first mango, it is going to be total number of mangoes over the total number of fruits we have. The total number of fruits we have in the bag is 3 plus 2, which is 5. So for mango, the probability of picking the first mango is now 3 over 5. Now remember that anyone you pick, that one is gone. It is lost. You can't put it back. Now picking the second mango, because the first one you picked is lost already, you did not put it back. It means that the total number of fruits in the bag has reduced from 5 to 4 because you have picked one before and you did not put it back. And also, the total number of mangoes has reduced from 3 to 2 because in the first one you picked mango and you did not put it back. So we now have a reduced sample space. The sample space now is 4 and the number of mangoes available now is 2. So we now have 2, which is the event we are looking for, over 4, which is the sample space. So this gives us 1 over 2. Now remember that the formula for dependent events is probability of the first event and second event is equal to the probability of the first event times the probability of the second event. So we just multiply the 2 probabilities, which is 3 over 5 times 1 over 2. And this will give us 3 over 10. So that is why we have this. Now let's look at B. In B, we are selecting probability that the two fruits we pick first, the first fruit we pick is mango, and the second fruit we pick is orange. Now we start with mango. Picking mango for the first time, we have 5 fruits altogether, and out of the 5 we have 3 mangoes and 2 oranges. So if we pick a mango, we are picking, the probability is 3. That is the total number of mangoes, 3 over the total number of fruits, which is 5. Now, if we want to pick again, the total number of fruits has reduced from 5 to 4 because of the mango you picked before. So it has reduced. Okay, so we now have 4 fruits altogether remaining because of the mango we picked without replacing it, and our orange still remains 2. So we have 2 over 4. It is now 4 because we have taken 1 mango out from the bag without replacing it. So the probability of picking an orange is 2 over 4. Now we use the same formula for dependent events to get the sum of the probabilities, which is the probability of the first is mango and second is orange. So we have 3 over 5 times 3 times 2 over 4. So this gives us 6 over 20, which is now 3 over 10. So that is why we have this as the answer. Now, example 2. We have the same question. A bag contains 3 mangoes and 2 oranges. If 2 fruits are taken from the bag at random with replacements, here calculate the probability that the 2 are mangoes. The first is mango and the second one is orange. We pick here with replacement, which means that we pick the orange from the bag and maybe we get another orange and put it back. And if we pick a mango, we get another mango and we put it back, or the same mango, we put it back. So there is a replacement in this case. For the question A, if the probability of picking 2 mangoes. Now, the first time we are picking the mango, we have 3 mangoes and 2 oranges. That means sample space is 5. That is now the total number of mango over the total number of fruits, which is 3 over 5. Now, in the second event, because we put the mango back to the bag, replacements, remember, we put it back, it means that the total number of mango is still remaining the same. So the probability of picking another mango still remains 3 because the mangoes remains the same over 5. The fruits, the sample space remains the same. So it's now 3 over 5 again. So our probability now is 3 over 5 times 3 over 5, which gives us 9 over 25. So you see how this one works, because we place back the fruit taken, the sample space remains the same. Now let's solve B. You will notice something here. Now in B, the first time we are picking mango, and the total number of mango then is 3, and the total number of fruits is 5. So we have 3 over 5. Now the second one we are picking is mango, is orange. The total number of orange available is 2, but we have put back the mango we picked before, so making the number of fruits to remain the same, that is 5. So we now have 2 orange divided by the total fruits, which still remains 5. So we have 2 over 5, and that is why our probability now is 3 over 5 times 2 over 5, which gives us 6 over 25 as the answer. So you can now see that the dependent event without replacement and dependent event with replacements will always give us different results. When you are given questions to solve, you should be careful enough to notice whether it is with replacements or without replacements. So that is what we have in this lesson. We've talked about the definition of dependent events, the types of dependent events, expression for dependent events, and then we solved examples showing how to work around with dependent events with replacements and dependent events without replacements. And I hope that the lesson is very clear. Thank you.